So let me just remind you where we're at in the class right now. We've been talking about arrow pushing as a representation of the filled canonical frontier molecular orbitals with unfilled molecular orbitals, and specifically frontier orbitals. And we talked about the 6 canonical types of frontier orbitals. If you want to add electrons to something or attack something, your arrow pushing is going to be ending either at a sigma star orbital, you break a sigma bond, a pi star orbital, you break a pi bond, or some empty p orbital like a carbocation or a borane. And your arrows will start, the curved arrows that you draw will start with some sort of filled orbital or something that represents a filled orbital in your Lewis structure. So a non-bonding lone pair, for example, or a pi bond. And then last, the lowest in energy, the least nucleophilic bond type that we have in organic chemistry should be a sigma bond. And you can just look at the energies of s and p orbitals and understand this relative ordering here. So it says that we should expect sigma bonds to be not very common as nucleophiles. And what I want to talk about over the next 2 lectures is what would you need to do in order to make a sigma bond nucleophilic enough to react as a nucleophile in an organic reaction. So, and you've seen these kinds of reactions in sophomore organic chemistry in last quarter, and that's what I want to talk about. So I'm sure you've seen examples of organometallics acting as nucleophiles and attacking things. I'm sure, well, you may not have seen examples of carbon-hydrogen bonds acting as nucleophiles. What would it take to make a carbon-hydrogen bond nucleophilic enough for that to act as a nucleophile? And I have not seen an example where a simple alkyl carbon bond acts directly as a nucleophile and attacks something in an intermolecular process. There must be something that special about these 2 cases that allows those to act as nucleophiles. So I want to start off by getting everybody comfortable with the periodic table. As an organic chemist, I don't spend much time thinking beyond these 3 atoms right here. That's most of organic chemistry. So what are the periodic trends that I expect you to understand and apply all the time? Very powerful periodic trends. I'm going to start over here at the top. The first row of the periodic table, there's not much there, basically hydrogen atoms. Hydrogen atoms are very small, low in mass, they vibrate very quickly. Just look at an IR spectrum. CH bonds vibrate 3-4 times faster than CC or CO or CN bonds. And if things are moving faster, it's easier for those things to transfer. It's easier to break carbon-hydrogen bonds, it's easier to, they're just more mobile. So expect it to be easier to attack H's than to attack C's and break bonds. It's just easier to move an H from one atom to another. That's easier than doing SN2 at carbon. Okay, so things are faster with protons. When we drop down here to the second row of the periodic table, there's something special you can do with second row atoms that you can't do with any other row. Not the first row atoms, not third, fourth, fifth. They make stable pi bonds. Relatively stable pi bonds. The p orbitals can get close enough together where you can have stable pi bond formation. And what we'll see on Friday and early next week is when we drop down to the third row or lower, you don't get stable pi bonds anymore. Even if you've got a minus and a plus and a lone pair right next to each other, they're just too far away. Filled and empty orbitals will be too far away to get effective pi bond formation. And that has immense implications for reactivity. And then again, as we drop down to this third row or lower, the bonds are longer, they're weaker, orbital overlap is less effective, and so the bonds that you get aren't low in energy, they're high in energy, and they're more nucleophilic. So long bonds are more nucleophilic and more easy to break. Okay, so what I've got here is a periodic table with the electronegativities on there. And I'll fess up to you and tell you, I basically remember I remember one electronegativity value, and that's carbon. I just remember carbon has an electronegativity of 2.5. But you know what? I can guess what the electronegativity of nitrogen is. Let's walk over here. It's 3.0. How about oxygen? It's 3.5. Right? There's this monotonic increase in electronegativity as we march across the all-important second row of the periodic table. If you can just remember the electronegativity of carbon or fluorine or any one of those, these all differ by a half a unit. And the reason why there's this monotonic increase, 2, 2.5, 3, 3.5, is because all these atoms are about the same size. That's why. And the only thing that's changing is you got one more proton added to each one of these as we march across here. So it makes it very easy to understand changes in reactivity as you go across this second row. And that's not true for the other rows, and it's not exactly true when we come back over to this end, although it's not a bad
it's not a bad estimate for you to keep subtracting half an electronegativity unit as you walk over to lithium. Berylliums are a little bit weird, but it's radioactive, it's toxic, it's expensive. You're never going to see that in organic chemistry. So I wouldn't even worry about BE. Okay, so simple periodic trends. The electronegativity, I think you know. You learned this in first year freshman chemistry. Increases as we go up this diagonal of the periodic table. The most electronegative element in the periodic table is fluorine. You won't see a lot of fluorine chemistry in academic chemistry. Super important when you get to industry, and specifically the drug industry. And then things become electropositive as we move back over to your left side of the periodic table and then down. So very electropositive. Those atoms don't really want electrons as much as carbon. And the important thing is for you to measure things relative to carbon, because this is an organic chemistry class. Okay, so I'll show you one more. We'll talk a little bit more about periodic trends in just a moment. But let me just come back to this idea of canonical frontier orbitals. And let's talk about bonds to carbon, single bonds to carbon. When you draw out a bond to carbon between carbon nitrogen or carbon lithium or carbon boron, you know, those are just not very nucleophilic orbitals. The pi bonds and the lone pair orbitals are way up high in energy and very nucleophilic. But if I go from a typical atom like a carbon-carbon, carbon forming a bond to carbon, and I decrease the electronegativity, boron to beryllium to lithium, electrons really want to be in orbitals that are associated with nitrogen or electronegative atoms. But when I go to an electropositive atom, I can make this orbital, this canonical orbital, that bond, reactive enough where it can become as reactive as a lone pair or a pi bond. So this is a huge effect to march up here to go to a carbon-lithium bond. So lithium is very electropositive. So when I stick an electropositive atom like lithium onto carbon or oxygen, that bond can become nucleophilic enough to engage in chemistry. But if I'm making a bond to lithium or potassium to some heteroatom like oxygen or nitrogen, and there are still lone pairs on there, those lone pairs are still more reactive than the bond. Right? The effect of lithium is not only to make this bond right here more nucleophilic, but that electropositive atom also makes the lone pairs more nucleophilic. So continue to use the lone pairs when you have lithium attached to oxygen or nitrogen. You'll see that with LDA, lithium diisopropyl amide, with alkoxy lithiums and other types of alkoxides, metal alkoxides. Okay, so we've talked about the periodic table, and we've talked about electronegativity. And what I want to do is look at size. This idea that when you drop below the second row of the periodic table, so here are these wonderful second row atoms, boron, carbon, nitrogen, oxygen, fluorine. What's the take-home lesson? They're all about the same size. Wow, that's wonderful. We can sort of reduce all of our understanding here just to electronegativity and not have to worry about size much. But when we drop down below that second row, it's just hard to make pi bonds. The p orbitals are big enough to where you just don't get effective overlap when you align p orbitals with a second row atom and a third row atom, or a third row atom, a third row atom. They're just too far away. You don't get effective pi bond formation. So what happens when I make a bond between carbon and lithium? Let's walk over here. When I march over to this part of the periodic table, it's not the same size anymore. Lithium atoms are bigger. The orbitals are bigger. If you were an electron, would you really want to spend much of your time close to a nucleus that doesn't have a lot of electrons in it? No. You'd want to be far away from that nucleus. You'd want to be closer to a carbon nucleus. So when you make a bond between carbon and lithium, it's not just that lithium is electropositive, but the bonds are longer. The electrons will spend their time farther away from the lithium and not held as tightly. So when you make a carbon-lithium bond, those bonds are very nucleophilic because they are longer and they are weaker. So that's the impact of size. And if you want to make bonds even longer and weaker, go down the periodic table. Lithium, sodium, potassium, that's radioactive, forget that, cesium. So just remember this, so about the same size, pretty much, for all intents and purposes as far as this class is concerned. But then things get bigger and way bigger as we drop down the periodic table. Okay, so let's. I'm going to show you one set of pictures before we start. Before I start the lecture, just so we can talk about bonds to metals.
And what I want to do is I want to look at some structures, some real, I guess, more real than the things I'll draw on the board, some structures of bonds to metals, alkali metals. Lithium, sodium, potassium. Here's sodium hydride. How many of you in here have worked with sodium hydride before? Yeah, most of you have worked with sodium hydride, done something with it. It's a gray powder that stirs around at the bottom of your flask and does not dissolve. Sodium hydride is not soluble in anything. It doesn't dissolve in any solvent. If you see it dissolving, that's because it's reacting. So here's the chemical structure for sodium hydride or potassium hydride. Lithium hydride's the same. It's a cubic lattice. In other words, these bonds that are on the inside of the lattice are not reacting with anything. There is no reaction occurring with the bonds in the center of these massive crystalline lattices. All of the reactivity of those hydride reagents is on the surface of the reagent. Calcium hydride is just crazy, but it's the same idea. Stuff on the inside, it's not soluble. Stuff on the inside doesn't react. It's all reactions on the surface. Let's take a look at butylithium. If you get a crystal structure, and I just put this here a few minutes before lecture, so I didn't have a chance to get a better structure. But here's a carbon atom, and look at all the lithiums on there. When was the last time you drew butylithium like that when you were doing an arrow pushing mechanism? That's what happens when you get solid butylithium and you take a look at it. Let's take a look at this potassium alkoxide here. This is potassium T-butoxide. This is one of the first alkoxides we show people in sophomore organic chemistry here at UCI and at most schools. How many bonds does oxygen want? How many free lone pairs are there on oxygen in that structure for potassium T-butoxide? If we come over here and we look at a lithium enolate, you're probably doing lithium enolate chemistry in Chemistry 204 synthesis, the graduate course. Right? When you look at the oxygens, right, I have a tendency to think about lone pairs on that oxygen, but when you look at the real structure for a lithium enolate, how many lone pairs are there on oxygen there? So we're going to talk about arrow pushing reactions, and we're going to show structures, but I want you to keep these ideas in mind, this idea of aggregation, and the fact that lithium really demands to have an octet, or at least get as close to an octet as it can. You know, if you want to draw lithium with no bonds, you're closer to reality trying to draw lithium with 3 or 4 bonds. That's closer to reality. So just keep that in mind. Okay, yeah, the octet rule does not disappear just because we are working on the left-hand side of the periodic table. Okay, so let's get down to some drawing out some reactions. So let me try to summarize what I just showed you with those periodic tables that I showed you. We don't have to memorize the whole periodic table or all the electronegativities of everything in the periodic table. And I'll just summarize by saying that, that electronegativity determines 2 things that are sort of the converse of each other, or are maybe they correlate with each other. So I'm going to draw out a series of atoms here, and then we can summarize the electronegativities and the properties of these. And so again, in the periodic table, this would be the alkaline earth elements as we march down. Magnesium is the exception. That's 1 over. But all these others occur in the same column of the first column of the periodic table. So I'll start off by drawing out the covalent radius. I'm going to enumerate that for each of these atoms just to remind you of the sizes of these. If you were an orbital, a 1s orbital on each of these, how close would you want to be to that atom? How big? So I'm going to start off with a hydrogen atom. The radius is very small. You know, a typical carbon-carbon bond is about 1.5 angstroms long, but carbon-hydrogen bonds are shorter. I come over here to magnesium.
And a bond between carbon and magnesium is much longer than a bond between carbon and a hydrogen atom. Similarly, if I make a bond between carbon and lithium, that's also longer. And it's about the same length, the same long length as a bond. And this is just the radius, so the actual diameter would be twice that, right? That's the radius I'm giving you. So if I make a bond to sodium, it's going to be a longer bond. Bonds between carbon and lithium and in carbon and sodium are different. Carbon-sodium bonds would be a lot longer than a carbon-lithium or a carbon-magnesium bond. And as I keep dropping down the periodic table, if you think about the periodic table, these atomic radii are going to get bigger and bigger. Okay, so the bonds to these elements just spend they're farther and farther away when they're bonded to carbon. So underneath here, I'm going to summarize the electronegativity values that I just gave you. So protons have electronegativities between 2.1 and 2.2. Remember, carbon's 2.5. So it's actually a little bit closer to the electronegativity of boron than it is to carbon. But it's really, a carbon-hydrogen bond is really nothing like a carbon-lithium bond. If you look at the electronegativity for magnesium, right, that's really very electropositive. A proton is kind of positive, more so than carbon, but these types of metals are very electropositive. Lithium, sodium, potassium, cesium, super electropositive metals, super long bonds, they just cannot get close to carbon. And so the end result here is that when you look at this property, I'm sorry, I've got this sort of MO diagram here that's getting in the way. So when you combine these two things, the closeness that how close can these atoms get to carbon, and the electronegativity, it allows us to summarize how much ionic character there is in a bond to carbon. So if I look at a bond between carbon and hydrogen, I'll just use R as my symbol for an alkyl group and a bond to carbon. That's really covalent. There's not much that's more covalent to that than maybe a carbon-carbon bond would be more covalent, but that's a pretty pure covalent bond. Then when I make a bond to magnesium, and as I keep marching across here on the periodic table, these bonds will become more and more ionic. I'm not even sure how to, I really hate to use dashed lines because you can't push arrows with dashed lines. But eventually I'm going to get over here to this alkyl cesium bond, and here I'm just going to have a tendency to draw things like this, where it's purely ionic. They're just two things that are close to each other. At some point, my description is going to be a lot of negative charge on carbon and a lot of positive charge on the metal. So these bonds over here are very covalent. These bonds, as I get over here, alkyl potassium, maybe I'll draw a delta plus, delta minus here, very ionic. And why does that matter? Because one of the most important reactions in organic chemistry, which is deprotonation, proton transfer, involves attacking protons. And that is mainly driven by charge. So ionic character, let me go ahead and just draw this. Ionic character keeps increasing and increasing and increasing, and is the highest with some sort of alkoxy-cesium or alkyl cesium reagent, if you could make it. What I'm really seeing is an increase in basicity as I move towards the right. Right? You don't use alkyl hydrogen bonds as bases. Methane isn't a base. But if you could make methyl cesium, that would be a screaming, white-hot nuclear base. Not nuclear, but very reactive, super-duper reactive. Okay, so more ionic bonds will be more basic, super basic, and those reactions will be driven by Coulomb's law and charge. Okay, let's take a look in some real reactions. Okay, I'm going to draw out a carbonyl compound.
And I'll take this simple ketone, acetophenone. Just a ketone. There's a phenyl group on one side and a methyl group on the other side. And look how careful I was to draw the alpha protons here. Because if I come along with some sort of organometallic reagent, like a Grignard reagent, phenyl magnesium bromide, phenylithium, for example, we have a choice. One choice would be to have this bond come in here and attack pi star. That's a reaction that's driven by the fact that the LUMO is low for pi star. It ought to be easier for me to dump electrons into a pi star orbital for a CO bond. The result of that would be that I would make this new bond between the phenyl and the carbonyl group. But there's an alternative reaction that you could have. And it's driven by the fact that there's a lot of partial positive charge. If I look at where most of the charge, the positive charge, is located on a molecule like this, it's actually on the protons. Protons are more electropositive than carbon. And so there's a strong driving force to attack this proton and then let those electrons donate into pi star. And the more negative charge you put on this group, phenyl, the more likely you are to deprotonate. Which really, that doesn't do anything in your reaction. When you work up the reaction for the enolate that you would get. So if you pull the proton off, you'll simply get an enolate out of that. And when you work up your reaction, it'll just turn back into the ketone. It'll protonate to re-give you the ketone. And it will look like nothing happened when in fact you had a very major side reaction. Let's take a look at the ratios of attacking pi star versus sigma star. Whoops. Sigma star for that CH bond. In other words, deprotonation alpha. What are the ratios of those? I'm going to start over here. If my reagent is a Grignard reagent, let's come back over here to our series. Of these types of reagents, a bond to magnesium is one of the more covalent types of organometallic bonds. So when I look at a bond between carbon and magnesium, you get a 97% yield of the Grignard reagent. And you don't get any of the deprotonation. When you do organometallic additions in sophomore organic chemistry laboratory, they have you work with Grignard reagents because they don't want other side reactions occurring. That's one of the major reasons. That's very effective and it's very good. There's not a lot of partial negative charge on the carbon that's attached to magnesium relative to the other reagents that I'm going to show you. So if I make a bond between phenyl and lithium, that ratio now changes. Who would have known? You get a 75% yield, or sorry, deprotonation starts to become a major problem as we make the carbon more negative and the metal more positive. So I'll drop over here to phenyl sodium. You've never seen anybody work with phenyl sodium, and this is why. It's way, way basic. Yeah, it's nucleophilic, but the basicity just totally takes over. Totally takes over. And finally, if you, again, there's also a problem which is making these reagents, but if you get to phenyl potassium, the bond is so ionic. There's so much negative charge on carbon, it just goes all for the protons. You don't even get any. You don't get any nucleophilic addition to the carbonyl with a potassium reagent. It just pulls protons off of stuff. It's looking for charge. It's not looking for, the charge dominates so much, it's not looking for any LUMO. That's kind of secondary in character. Okay, so you make things you make carbon really, really anionic, and you really make charge an important factor as you make longer, weaker bonds to electropositive metals. Okay, so that's carbon-metal bonds. Let's go ahead and talk about let's go ahead and talk about bonds between metals and hydrogen. Okay, so let me just remind you that these hydride reagents, lithium hydride, sodium hydride, those brown grayish powders or grayish powders that never dissolve in your reaction, actually exist in cubic lattices. Each one of those little particles looks like this, basically, something like this. Here's sodium hydride. And I can't draw an infinite cubic lattice, or nearly infinite, but you can just imagine just a nearly infinite lattice. That's the structure for sodium hydride and potassium hydride. Lithium hydride, calcium hydride is not exactly cubic, but it's still heavily aggregated like that. And so how are we going to deal with that? When you do a reaction where you use sodium hydride as a base, here's how we're going to deal with that. We're just going to pretend it's a monomer. But every time you draw that monomer, we're just going to agree, we're all going to remember that all of these hydride reagents look like these cubic lattices. So when you do arrow pushing, I want you to do this. Just like you've been doing. Right? If you use sodium hydride to deprotonate something, and I ask you what the arrow pushing mechanism is, I want you to continue to do exactly what you've been doing. But every time you do that, I want you to remember, well, that's not really true. Right? That's not really what sodium hydride, it's not like a molecule of NaH floating around in my reaction mixture obeying standard laws of kinetics. It doesn't work like that. That's not how it works. It's all occurring on the surface of those little particles. Meaning the finer you grind your particles, the more surface area there is, and the faster you'll get deprotonation. Okay, let's talk about the speed of deprotonation. And finally, we can put some numbers on what happens as we go from lithium to sodium to potassium. Let's go ahead and talk about let me make this more generic by just having the letter metal here. In the early 1960s and before, so before the 1960s, we didn't have LDA as a way to make enolates. You had to use some other types of highly basic materials or reagents in order to make enolates. And so what did they have? The list of reagents wasn't very big. And so let's just take a look at the speed of hydride reagents. They've been around for a long time. So if you deprotonate to make an enolate, the byproduct here is going to be hydrogen gas. So you add to some sort of CH antibonding orbital, sigma star, and that donates into pi star, and you make an enolate out of that. It's the same arrow pushing you learned back in sophomore organic chemistry. And what I want to do is I want to draw a little table here where we compare the reactivity of hydrides and the rates, the relative rates. So not the absolute rate constants. Here are some relative rate constants. And I'm arbitrarily going to assign lithium hydride to a relative rate of 1. It doesn't matter what the units are. Like, is it 1 mole per hour or 1 mole per second? The important thing is that if you take the lithium hydride out and you replace that with sodium hydride, your reactions will be 1,000 times faster. That's why you've never seen anybody do anything with lithium hydride. If sodium hydride, if your reaction takes an hour with sodium hydride, you're going to be waiting 1,000 hours for the reaction with lithium hydride. You don't have that kind of time in the lab, in graduate school. Right? And if you really are gutsy and are willing to work with something that's reactive, and you value your time, then you're going to switch to potassium hydride. Right? If you've worked with potassium hydride, you've probably had a fire, just to give you a sense for how reactive that is. Right? When you quench it, you add some you add some solvent, isopropanol to quench it, and then you get impatient and you add water and it instantly flames up and starts the hexanes on fire every time. But the advantage is that it gets the job done very quickly on your substrate. So that's what happens as we move down the periodic table. This gives you a quantitative sense to what's happening as you go from lithium to sodium, potassium. And you're just increasing the amount of charge on that H. So charge starts to really become this dominant force. in accelerating reactions. Come back to bonds to carbon and metals, alkali metals. They aggregate. That's those pictures I showed you. It was intended to get across the idea that when you make bonds to lithium or sodium or to potassium, there's always some sort of an aggregation. And what's up with that? If you make a bond to lithium, butyllithium, that lithium is not happy with just one bond. It's not. It wants to satisfy the octet rule just like all the other second row atoms. Let me, I showed you this sort of a crystal structure of butyllithium THF complex. I'm going to try to sketch it out using the whiteboard here. So I'm trying to draw a part of butyllithium. If you take butyllithium in THF, what does it look like? I'm going to start off by just drawing this sort of cube of carbon-lithium bonds, and then I'll fill in the blanks because this is going to be butyllithium. I'm drawing. This is what happens when you put butyllithium in THF. So I've got a square on top, carbon, lithium, lithium, carbon. These bonds are in front, so I'll just kind of make them a little bit darker to make it look a little bit three-dimensional. And in back, got another square back there. There we go. So I've got a cube of butyllithium, of carbon and lithium bonds. Each one of these corners here is a butyl group. I'll just draw the other carbons in that butyl group. There's 4 carbons in butyl. And then when you look at the lithium, each one of these corners of lithium, it's not happy in THF. Lithium is not happy with 6 electrons. When you put butyllithium in THF, the corners are occupied by a THF. Now the lithium, and you just have to amplify, all the corners look like this. I'm only doing 2 corners because otherwise this looks too crazy. Wow, that's crazy. What's up with that? And just to help blow your mind a little bit more, let me keep drawing what's attached to this carbon that I didn't completely draw. There were 2 hydrogens there, and they're still there. That's the structure of butyllithium in THF. How many bonds are there to carbon? The important point of this structure is that it doesn't violate the octet rule. The carbon still only has 8 electrons. It's sharing them with a lot of atoms. You may think that there's some rule that says, oh, you can't have more than 4 bonds to carbon. That's ridiculous. Of course you can. You just can't violate the octet rule. That's the rule that you can't violate. It's the octet rule that you can never go beyond. So when you put butyllithium in THF, it's actually an equilibrium of aggregates that are floating around in solution. So what you have to imagine, just imagine this bottom part of this cube lifting off. And I'll redraw just the bottom 4 atoms in that cube. I'm trying to make this kind of 3-dimensionalized here, so I'll try to, the bonds that are closer to you, I'll draw dark. So you can imagine if I lift away this bond over here on the edge and I replace that with another THF molecule. Actually, let me put the THFs over here. Right, so here's another way you can help each one of those lithiums satisfy the octet rule is you can use 2 THF molecules instead of just 1 on each lithium. So here's my butyllithium. Here's my butyllithium. And then each one of these, I'll just put X over here for more THF molecules. So one way to help lithium satisfy the octet rule is to make this cube and then have one THF bind to that corner. But if you just lift off these atoms on the bottom and put another THF there, you can still, the bottom line is that lithium, right, when you draw
this is a picture, this is the true picture of butyllithium in THF. So when you draw this with a butyl anion next to it, right, which one of these is closer? I mean, these are reality. But if you draw this, right, is lithium really happy with 0 bonds? No. No, lithium wants to have an octet of electrons. Okay, so this is awful. How are we going to deal with this? Okay, butyllithium is so heavily aggregated. When I ask you to draw the arrow pushing mechanism, and I draw butyllithium out as a reagent, and THF is the solvent, which it always is, not always, but most of the time, let's take one of the simplest reactions that we can imagine, and that is the reaction of a ketone with an alkylithium, like methylithium. So here's a ketone. So lithium wants to have lone pairs poking into it. There's lone pairs on THF. That's what happens if you take methylithium, for example. So you can imagine as you've got this tetramer floating around, a THF molecule pops off, and the lone pairs from a carbonyl on your carbon can reattach. So this is one of the species, and I have to make the charges match here. I'll do it like that. And so there's this initial, and I'm not drawing all the other stuff. There's THF molecules coordinated to these lithiums. I'm kind of, okay, this is not the, I'm simplifying this because it gets to be too complex. What I'm going to do is I'm going to take these electrons off of here and give them to the alkyl group. And so now I'm going to end up with this structure where I've got plus charges here. I'm going to have to make a point in a second because I'm doing something here that actually I was doing it over there, and I have to make a point as to what I'm doing over here that might look crazy, but it's not totally crazy. And then, after that 4-membered ring opens up, then this transfers an alkyl group to a rather nice 6-membered ring transition state. And all this other stuff is still attached on here. Okay, what was I doing here that, and I apologize, I didn't make this clear before. And what's up with these charges that I suddenly decided to draw in there? What I was doing with this structure over here, is I'm using something called a dative bond. And so let's talk about dative bonds. So for example, if I draw a Grignard reagent like this, and I draw ether molecules on there that are coordinated. When you put Grignard reagents in ether, it's just like alkyl lithiums, they coordinate. The magnesium has ether molecules that are coordinated to this. And when I draw it like this, I'm using dative bonds. How do I know that those are dative bonds and not regular bonds? The important thing here is that a dative bond is not part of the Lewis structure formalism. And since it's not part of the Lewis structural formalism, do not use them for arrow pushing. Do not use dative bonds for arrow pushing. Watch what happens if I try to take one of these bonds and use it for arrow pushing. Okay, I'm going to dissociate one of those ether molecules. Now, as I've drawn it here, if this was a Lewis structure, what I'm claiming is that magnesium is neutral and oxygen is neutral. Right? If this really is a Lewis structure, I didn't draw a charge on magnesium or oxygen. And therefore, if I take 2 electrons and I give it to the ether, I have to give that ether a negative charge. And I have to give the magnesium a positive charge if I take 2 electrons away. And we know that is not the charge. I promise you that's not the charge on diethyl ether in the formal Lewis structure. right? This is where things break down when you use dative bonds for arrow pushing. Your charges will be all messed up. So dative structures don't take account of charges. If I wanted to draw a Lewis structure for this using the Lewis formalism, I would have to put -2 on magnesium. Each pair of electrons that I poke into magnesium is going to add a minus charge. It would be an 8 complex, a magnesiate, 2 times over. So this doesn't take account for charges. Those are dative bonds. Let me just draw here. These are dative bonds right here. And that's what I was doing over here. It starts to get really bad when you start to put 3 negative charges here and all the charges. It just becomes too crazy. Okay, so be careful. Never use dative bonds for Lewis structures. This is what they do in organometallics with phosphines coordinating to metals. It just becomes too bothersome to draw all the charges there, so they're not using formal Lewis structures. They draw things with dative bonds. And I'm using dative bonds here just because when you start to draw negative charge, and counterbalancing positive charges, it just becomes too mixed up. Okay, so how are we going to deal with all this aggregation? I was about to say aggravation. Maybe that's the best way to describe that. I'm just going to ask you to remember it, that things aggregate. And just keep pushing the arrows the same way that you've been already pushing them. But just remember that there's aggregation going on. And suddenly, when you can't explain what's going on in your reactions, maybe they're giving you some result that you didn't anticipate ahead of time, then you can fall back on the fact that, oh yeah, those things aggregate in solution. And this fiction that we're drawing, when we draw this stuff, is actually just a shortcut. So if we all agree that we're going to remember that alkyl lithiums and alkyl sodiums, or if you could see those things aggregate, then it's acceptable for us to draw alkali organometallics as monomers, even though they're not. Remember that metal's not happy. For the typical metals, that's lithium and sodium, etc., they're not happy with just 2 electrons. Okay, so we're going to pretend that these species are monomeric, even though they're not. Okay, let's talk about metal alkoxides, like this, like the one we just finished making, right here. They aggregate too. That was that picture I showed you. They always aggregate. Any solvent you pick, there's going to be aggregation of those. You can diminish it if you go to superpolar solvents, but there's going to be aggregation. And I don't even know if I can draw. I'll start off with the T-butoxide. And I'll just tell you, whatever you drew in sophomore again, no, that's not right, right? That's not right. When you put it into solution, you find that here's the structure for potassium T-butoxide. And I'm not going to draw the whole thing. It's just this big cubic thing, just like I showed you before, a cubic shape. I'm not filling in everything. There's no free lone pairs on the oxygens. Each one of those is bound to a potassium. And if you've got a coordinating solvent in there, the corners of the potassium corners have something else coordinated to them. That's the structure of potassium T-butoxide. Okay, so let's talk about some arrow pushing using alkoxides. So the truer picture for potassium alkoxides, certainly lithium alkoxides, is heavy-duty aggregation. I was going to draw a picture of a lithium enolate, but it's a hexamer. Right? We don't have time for me to draw that hexamer out, just to give you a sense for aggregation. Okay, let's talk about how to deal with mechanisms for species like this. Remember what I told you. When we go from a carbon atom to something like lithium or potassium, this bond, this oxygen-nitrogen bond, becomes more nucleophilic. But at the same time, when I bond oxygen to something that's more electropositive than carbon, the lone pairs also become more reactive. And it's the lone pairs that are reacting in these types of species. So for example, if I do some sort of an SN2 reaction, I want you to use the lone pairs on oxygen. That's the more nucleophilic part. Once you start using sigma bonds to attack stuff, you're going to be totally misguiding yourself. So sometime in the future, you're going to make mistakes about what's the more reactive part of a molecule. And so the product that you get out of this arrow pushing that I just showed you looks like this. That sodium is still attached there, and now you have to get that sodium off of there. So my arrow pushing tells me if I make one more bond to oxygen, it's going to be an oxonium ion. There's going to be a positive charge on oxygen, and this bromide will now be floating off. And so how do I get from that species? Let me draw the bromide up here seductively to make it look like you're ready to just SN2 that sodium. Do not draw an SN2 reaction at sodium, I guess is all I want to tell you. Don't draw a direct displacement. Right? The only reason you draw SN2 for everything is because that's the first reaction you learned in sophomore organic chemistry, and it's always the first thing that comes to mind. The sodium does not leave that oxygen through an SN2 process. And it's not to say that the sodium doesn't come off. What would be a good way to make that sodium come off? I mean, how many bonds does sodium want? Lots. More than one, that's for sure. And so it shouldn't be crazy at all for you to do this. And don't break the sodium-oxygen bond when you attack the sodium. You shouldn't be made uncomfortable. Now, by drawing 2 bonds to sodium, I just showed you a bunch of things where there's 4 bonds to potassium and sodium and lithium. That's a little happier, still not completely happy. And don't freak out because there's 2 bonds to sodium. Perfectly good. It's all good here. And then in a second step, we can break that sodium-oxygen bond. And at no point was there sodium floating around or SN2 reactions going on. So that would lead to sodium bromide as a byproduct. I would also accept, and it's not as good, but I would also accept this alternative mechanism. And I'll explain what I don't want you to do. I don't want you to do the SN2, but there's something else that I don't want you to do with sodium alkoxides or metal alkoxide bonds. The other thing that I would accept, grudgingly, and here's why this is okay, is in typical solvents like THF, DMF, alcohols, this is always coordinated to other oxygens. We're just not drawing it. If you're in water, there's 3, 4 other water molecules attached to sodium, as many as you can fit on there. So I would accept this if you wanted to find a way to get that sodium off of there. And what's the difference between this? This is just a simple dissociation. Right? I'm not doing an SN2 to take the sodium off. It just, again, part of this is why this might look a little bit uncomfortable is that there's lots of solvent molecules already coordinated to sodium. It's not just a naked sodium cation floating around. Okay, what don't I want you to do? Let's talk about, I don't want you to do SN2 at those metals as a way to get them off. I don't want you to simply dissociate neutral metal alkoxides like this. You might say, oh, well, I took some class and we always drew the alkoxides as anions. Right? You just need to take Coulomb's law and ask, how much energy would it take me to separate that oxygen potassium from 1.9 angstroms to infinite distance in space? And then multiply that by 6.02 times 10 to the 23rd, and you'll get some energy in kcals per mole. And it will tell you that this is just no way that this is going to occur. Right? There's nothing wrong with using this as your nucleophile or your base. Just use the lone pair that's already there. You do not have to dissociate them in order to claim that the oxygen's reactive. It's just as reactive here as if you drew it in this ridiculous way over there. Right? That's not going to happen in your reaction, so that's crazy. And I'm not telling you that you can't have draw O minus floating around in your reaction. Here's what I would allow you to do. If you draw out a mechanism for an alkylithium butyllithium, methyllithium, phenylithium attacking some carbonyl group, there's a strong driving force to form a new sigma bond there. And when you take the lithium away from the when you take this pair of electrons away from the lithium, you're going to leave a lithium cation. And again, the fiction here is there's other stuff coordinated to that lithium. You're not actually leaving lithium just floating around. So again, I'm drawing it like lithium plus, but the lithium plus has THF or some other solvent coordinated to it. So this would be okay. Just don't take two things and pop them apart. Don't take neutral bonds and dissociate them to give two plus and minus charges. That's energetically so expensive, it just is not realistic. Whereas here, the driving force is I'm forming a bond. It's not like I'm simply dissociating those two molecules. There's a big driving force for that bond formation. Okay, so I've got one last thing to talk about that will help us resolve this issue of aggregation. And it's this study by Andy Streitweiser at Berkeley that makes me breathe easier with all these shortcuts we're taking. And it has to do with the fact that all of these aggregates that you get with organometallics, alkali organometallics, are in equilibrium. So if you take this lithium amide base, lithium diisopropylamide, that will very quickly deprotonate at the alpha position to give you lithium enolates. So hopefully you're learning about that in synthesis class right now. And if you treat that with an alkylating agent, benzyl bromide, methyl iodide, allyl bromide, you can form bonds here at this carbon. This acts as a nucleophile. I'll take benzyl bromide as my example. SN2 reaction. Now, when you look in solution, only 1% of the lithium enolate exists as the monomer. In a THF solution that has the amine floating around in there, which is also still coordinated to the lithium. In fact, this is in equilibrium with all kinds of other aggregates. Let me get the arrows right here. In fact, most of this exists in this, under these conditions as the dimer. And I have to draw the dimer by first drawing out this sort of square structure. This helps get me oriented. So the lithium enolate under these conditions exists as a dimer mostly. Very little of it is this monomer that I drew out. So here's the enolate. And I'm not going to, I'll just draw a phenyl here. There's the enolate that's floating. And there's other stuff coordinated to lithium. I'm not drawing that. So very little of the lithium enolate existed as that monomer that I drew. But what Streitweiser showed is that even though only 1% of the enolate exists in this form, this is so reactive relative to the dimer that all the reaction proceeds through the monomer. It doesn't matter, and we're going to talk about this more when we talk about something called the Curtin-Hammett principle. It doesn't matter that most of your lithium enolate exists as this dimer. What matters is that the transition state is lower in energy when you proceed through the monomer. So the tiny amount of this that's floating around in solution is so much more reactive than this, more than 100 times more reactive, and all the alkylation proceeds through the monomer. So, alkylithiums aggregate, lithium alkoxides aggregate, sodium alkoxides aggregate, potassium alkoxides aggregate. They all aggregate. And in solution, they exist as mixtures of these aggregates. But because quite often, monomers can be more reactive than the oligomers, I don't feel so bad pretending that all of our reactions proceed through the monomer when we do our arrow pushing. I want you to continue pushing your arrows by drawing out monomers, just like you've been doing. Remember, there's the potential for aggregation. Someday that's going to affect one of your reactions, and it's good to keep that stuff in mind. Okay, so when we come back on Wednesday, we're going to talk more about nucleophilic sigma bonds, and specifically we're going to try to get away from alkali metals.
and talk about things like bonds to hydrogen.